another circuit object to talk about is battery. Let's define the battery. So a battery is a device that holds two conducting terminals at a constant potential difference through the power of chemistry. That's all that's going on. Standard battery, this is a 9-volt battery. You don't see these quite as often as like the AA and the AAA cylinder batteries. But in this case, the 9-volt battery, here's the two terminals. Chemical reactions happen in here to hold a difference, in this case, of 9 volts between the terminals. So one kind of looks like this, and they're shaped different so you can tell them apart and so that they can clip together. And one kind of looks like this. One is the positive terminal, one is the negative terminal. And we know that it's a 9-volt battery, so that means the potential difference it holds is 9 volts. When we're thinking about batteries and circuits, we have to think about where's the potential 0. So for point charges, we said, oh, the potential 0 will always be at infinity. When you're doing field theory, the potential 0 at infinity. When you're making circuits and devices, you can be a little bit more, you can put the potential 0 wherever you want. So it's more convenient to pick one of your terminals or one of your electrodes, make the potential 0 there. So in this case, we're going to say the negative side will be just called 0 volts. And if that's 0 volts, then this is at plus 9 volts. So potential is always a difference, but if you define as 0, then you can start defining absolute potentials relative to that 0. So let's think what's happening really in this region. Well, if we have 9 volts here and 0 volts there, we actually have an electric field in here. So every time you hold a 9-volt battery, you're wielding a little electric field between its terminals. And you can say roughly what it is. Well, it's about a magnitude of about 9 volts per centimeter right along that line. They're not parallel plates. It doesn't make a uniform field, but it does make some sort of a field. We can also think about the potential. Well, these are conducting electrodes, so they must have equipotential surfaces all along their surface. So here is the 0-volt equipotential surface. It's the surface of that terminal. And here is the 9-volt equipotential surface. It's the surface of that terminal. And we know then also that the potential is going to go down as we go along the field. So the 8-volt line is probably something like that. 7, 6, 5, 4, 3, 2, and then the 1. So we can actually do field theory inside of a battery if we really want to. So that is sort of a law of physics and chemistry, that the chemical reactions in here must hold these at a potential difference of 9 volts. What we're going to do now is we're going to break the laws of physics. Now, it's a little bit risky and scary to break the laws of physics. You never know what's going to happen. But we're going to break them somehow because we're going to set something up where two laws can't be true at the same time. The laws of physics and chemistry require that the terminals of the battery be at a different potential. But we also talked about how in a conductor, the surface has to be all at the same potential, right? Because it goes, all the electrons will move to make the surface all be at a constant potential. That's in fact why each terminal on the battery has to be completely at 9 volts and completely at 0 volts. Okay? We're going to do this with a little bit larger battery so you can see it better. So this is a 12-volt battery. Here's its two terminals. So this one is negative, we can call that 0. This one's positive, we can call that plus 12 volts. And this is our metal. So this is iron wire. It's 75 microns in diameter, so it's about the diameter of a human hair. You can't quite see it very well in the video, but I promise you that there's wire there. How else would I do this? There is wire there. There's wire there, okay? So I'm going to take this metal wire and I'm going to place it across the terminals of the battery. So we're somehow breaking the laws of physics. We can't have this be at 9 volt or 12 volts, this be at 0 volts, and this all be at the same, because we're going to make one essentially large conductor. So let's see what happens when we do it. Okay, it's very exciting. Okay, here we go. I'm really going to do it this time. Okay, Here we go. What happens when you break the laws of physics? Oh, whoa. The universe gets very upset when you break its laws of physics. Let's try again. Maybe the universe was just having a bad day. Let's make sure that's really the outcome of this. So we bring it down. And is it going to be 0 volts, 9 volts, 12 volts? What's it going to be? The universe says, nope, can't exist, has to go away. So the answer is no. Apparently, you just can't do this. Right? So it's impossible. So we have to figure out what's going on. Well, as I alluded to in our discussion of what's happening with the metal plates in a capacitor, whenever something looks wrong in physics, there's always an answer. You can always figure it out. And almost every time, the answer is you deviated from your model. Right? There's always some condition. Anytime you say something, there's always a condition. There's always a model. Well, here we have once again deviated from our model. And the way we've deviated is that we are no longer in electrostatics. Remember, the surface of a metal has to be at a constant potential in electrostatic equilibrium. And in this experiment, we are no longer in electrostatic equilibrium.